Hello, everybody. My name is Mei Yang. I'm from Center for Heat Treating Excellence at Worcester Polytechnic Institute. In this presentation, I'm going to talk about the post-processing of additively manufactured AISI 8620. One of these current CHT projects is heat treatment of additively manufactured parts. This presentation is part of this project. In today's presentation, I'm going to show the characterization work we have done on as received AM and wrought parts. In the present work, the AM parts were fabricated by selective laser melting. The post-processing we decided to conduct on AISI 8620 is carburization. Based on the characterization on the as received parts, to ensure the same microstructure of AM and wrought parts for carburization process. The normalizing was conducted on the as received parts before carburizing. So the selective laser melted and wrought parts were compared after normalization, which is the second part of the characterization for the present work. At last, we will discuss the carburized AM and wrought parts to see the carburizing effects on them. So that's the third characterization part of the current work. Yeah, basically the presentation is composed of three characterizations. First, the as received parts. Second, normalized parts. Third, that's the carburized parts. So based on three characterization, we are going to compare the SLM and wrought parts at the different stage. In the following slides, I'm going to show the characterization work we've done on SLM parts, selective laser melted parts, about chemistry analysis, Vickers microhardness line scan, optical microstructure analysis, SEM microstructure analysis, and XRD analysis on the sample. Also the porosity analysis on this part. This is the as received AM part. This part is fabricated by selective laser melting. After deposition, this part was stress relieved and sandblasted. And these three images on the right side show the surface from this part. The top one is the top surface, and the middle one is for the side surface. From this one, you can see the deposition layers, the layer by layer structure from the additive manufacturing. And the bottom surface, just you can see because it's cut from the substrate, so you can see like there is some like cutting. This is the as received AM part, which is fabricated by the selective laser melting. After deposition, the part was stress relieved and sandblasted. And the three images on the right side show the surface condition of different area for this part. The top one is for the top surface, and the middle one is for the side surface. You can see the layer structure, layer by layer structure for this M part on the side surface. And the bottom surface looks very different from the top surface because it's cut from the substrate. First, let's compare the chemistry of the powder and the selective laser melted part. The powder we are talking about here is the powder used to build up the current selective laser melted part. So, yeah, from our understanding, the chemistry of powder and the SLM part should be similar. However, they're different. The powder chemistry is from the certificate we got from GKN, and the chemistry of the SLM part is from the OES measurement. So we conducted several measurements on the SLM part and get the average and show here in this table. You can see the big difference is on the carbon concentration. So the carbon concentration in SLM part is much lower than that in powder. Okay. So it's about 27% lower than that in the powder. And this is not new from our current project. From our previous work, we found we have carbon concentration decrease for 20M-SR5 and AISI 5122. So basically, the decarburization occurred during the SLM process. The possible reason for the decarburization of selective laser melted part may due to the reaction between the carbon and the water or oxygen in the powder. And the other reason is maybe due to the reaction of carbon with the water or oxygen in the nitrogen, which is used as the inert shielding gas for selective laser melting process. To evaluate the uniformity of this selective laser melted part, the Vickers micro-hardness line scan was conducted on building and transverse direction respectively. On transverse direction, we also do XY and YX, two perpendicular directions. So you can see for these three different directions, the micro-hardness line scan are very close to each other. And the average Vickers micro-hardness for these three directions almost the same. So there is no big difference for the micro-hardness. This part is very uniform. We can see some micro-hardness fluctuation on these directions. It may due to the microstructure variation. So we can talk about that more later. The microstructure analysis was conducted by optical microscope, and we want to see the uniformity of the microstructure on different position of this sample. So for the transverse direction, we selected a sample from near surface, center of the sample, and middle between the surface and the center. So basically there are three different positions we checked, and you can see the microstructure is looks the same, yeah, very similar to each other. So for the building direction, we choose the position from the top, bottom, and middle. So you can see, yeah, there is no big difference on the microstructure between the transverse direction and building direction. So for the microstructure itself, it is uniform too. The microstructure analysis also conducted by SEM analysis. So SEM can give us a much higher magnification. That's why we can see the details of the microstructure. Again, we chose different positions from both transverse and building direction. And you can see for transverse direction, 3 different positions give very similar microstructure. For the building direction, they look very similar too. Based on the SEM image, we can see it looks like a tempered martensite. The microstructure looks like the tempered martensite. We also conducted the XRD analysis to identify the phases in this selective laser melted part. The XRD pattern consists mainly of BCC iron on both transverse and building directions. So the pattern for transverse direction is very similar to the XRD pattern on building direction, and will mainly see BCC iron. Combined with the SEM micrograph, this BCC iron is identified as tempered martensite. So during the selective laser melting, due to the fast cooling during the process, we get the martensite. However, the layer deposited before will be heated when we deposit the later layers. So the heat when we deposit the new layer will temper the previous deposited layers. That's why we get tempered martensite. The EDS elemental mapping was conducted on the as polished selective laser melted part to investigate the chemistry distribution on both transverse and building directions. This slide shows the EDS elemental mapping results on the transverse direction. Actually, we analyzed several different positions. This one just shows the typical elemental mapping results. It can be seen that the chemistry distributes uniformly, very uniformly on this transverse direction. So we didn't see any segregation or inclusion. This is the EDS elemental mapping on building direction. Similar to the transverse direction, the chemistry distributes uniformly on this direction too. As I mentioned, yeah, we selected several different positions and conducted the mapping. This is just the typical one, so we didn't see any inclusion or segregation on building direction either. We also use the optical micrographs to analyze the porosity in this selective laser melted part. This shows the optical micrographs we took for building direction. Actually, this is not just one micrograph. We have several micrographs and we put them together. So then we can analyze bigger area. After we have this optical micrograph, we imported into ImageJ software to count the area of the porosities. So we'll talk about that later. This slide just show like, yeah, there are two, you can see there are two SEM micrograph with higher magnification. That shows the different types of the porosity. Basically, there are two kinds of porosity. One is irregular shape, the other one is the round shape. In general, though, the irregular shape pores are much bigger than the round shape pores. That's because the round shape pores are due to the entrapped gas. However, the irregular shape pores are related to the lack of fusion or shrinkage during the selective laser melting process. So from the micrograph, the SEM micrograph of irregular pore, you can see there is some unmelted powder. As we mentioned, image J was used to count the area of porosities. So this slide just show like the pore size distribution, and we also calculated the percentage of the area fraction of pores based on this size distribution. You can see the area fraction of pores on building direction is 0.2% or about 0.2. It's not too much. Actually, the density of this selective laser melted part is very high. Similar porosity analysis was conducted on the transverse direction of this selective laser melted part. Again, we can see irregular shape pores and round shape pores. Yeah, so basically there are two types of pores for this part. The area fraction of pores for transverse direction is calculated as 0.165%. So it's very close to the building direction. So yeah, basically there are not the area fraction of pores not too much compared to the part. Okay, so the density of the part is high. In summary, for the as received selective laser melted part, decarburization was found during the selective laser melting process. So the carbon concentration was lower in the selective laser melted part compared to the powder we use for the M process. Then the micro hardness is uniform on 3 different directions. Also, the microstructure is uniform. It is tempered martensite for the as received SLM part. And the chemistry distribution is also uniform. However, some pores are found in the selective laser melted part. Based on the image J analysis, the area fraction of the pores is about 0.2%. It's not too much. So in the following slides, we are going to talk about the characterization of as received wrought parts. In this slide, the chemistry of the wrought part is compared with the selective laser melted part. The chemistry of both parts were measured by OES. So for each part, we measure several times and get the average composition and show in this table. So you can see the main difference is the carbon concentration. The carbon concentration of the wrought part is much higher than the selective laser melted part, as we mentioned before, which is due to the decarburization of SLM part during the selective laser melting process. We also did the Vickers microhardness line scan for the wrought part on transverse direction and rolling direction. Similar to the SLM part, the selective laser melted part, the microhardness variation can be seen on both transverse and rolling directions. But the microhardness on transverse direction is very close to the rolling direction, so there is no big difference on the microhardness for both directions. However, the average micro hardness of as received wrought part is much lower than the as received selective laser melted part, because that one is the tempered martensite. So let's take a look at what's the microstructure for this wrought part. This slide shows the optical micrographs of wrought part. For the wrought part, similar to the as received selective laser melted part, we choose different positions on both transverse and rolling direction to get the optical micrograph. And you can see in general, the microstructure is very uniform on both directions. On the rolling direction, we can see the banded structure, but the microstructure is still similar to the microstructure on the transverse direction. So this microstructure looks very different from the microstructure for the selective laser melted part. And it looks like the ferrite plus perlite. Using SEM, we can get the micrographs with higher magnification. So you can see with the high magnification micrographs, we can see the perlite in the wrought part. The XRD analysis was conducted on the wrought part on both rolling and transverse direction for the phase identification. You can see the XRD pattern on rolling direction is very similar to the pattern on the transverse direction. So basically, they are the same phases. And also, we identify the BCC iron is the main phase on both directions. So combined with the optical and ACM micrographs, the microstructure of this 8620 wrought material is ferrite and perlite. So which explains why the microhardness of wrought part is much lower than the selective laser melted part, because this is ferrite plus perlite, but the microstructure for the selective laser melted part is tempered martensite. When we did the microstructure analysis by SEM and optical microscope, we found some inclusions on both transverse and rolling directions. That's why we conducted the EDS element mapping to confirm like the inclusions in the wrought part. So this is the element mapping on wrought part for the transverse direction. And you can see we have some inclusion which is manganese sulfide. The manganese sulfide inclusion is also confirmed on the rolling direction for the wrought part. And you can see the inclusions are along the rolling direction. Based on the characterization of the selective laser melted part and the wrought part, it was found the microstructure of selective laser melted part is tempered martensite, while the microstructure of wrought part is ferrite and perlite. So we decided to do the normalization process before the carburizing process to reduce the effect of the pre-carburizing condition. In the following slides, we are going to show the characterization results for the normalized selective laser melted and wrought parts. As I mentioned before, the AISI 8620 selective laser melted part was stress relieved and sandblasted after deposition. To investigate if the sandblasting on the surface affects the carburizing process, we put both selective laser melted, sandblasted, and unsandblasted parts for normalization and carburization process. So this slide shows the optical microstructure of the normalized selective laser melted part after sandblasted. You can see the microstructure change a lot compared to the microstructure we showed before for the as received selective laser melted part. It is still uniform on both direction, transverse and building direction. However, it looks similar to the microstructure of as received wrought part, which is ferrite plus pearlite. This slide shows the microstructure of the normalized selective laser melted part, which was not sandblasted after the deposition. So you can see basically the microstructure is similar to the microstructure for the sandblasted selective laser melted part, which is easy to understand because the sandblasted only affect the surface, it couldn't affect the core. This is the microstructure of the normalized wrought part. You can see it's actually there is no big difference between the as received wrought part and normalized wrought part. So it's still ferrite plus pearlite. However, like on the rolling direction, the banded structure disappeared after normalization. So after the normalization, both selective laser melted part and wrought part show the same microstructure, pearlite plus ferrite. So the only difference is on the grain size, but after we measure the grain size for these parts, we found there is no big difference on the grain size, just a little bit difference. Then the XRD analysis was conducted on the normalized selective laser melted and wrought parts to confirm the phases in these parts. The XRD pattern for selective laser melted part and wrought part, they are very similar to each other. So BCCI was identified and combined with the microstructure we showed before, this is ferrite plus pearlite in this material. The Vickers micro-hardness line scan was conducted on both transverse and building direction of normalized selective laser melted part. It can be seen that the micro-hardness of sandblasted and unsandblasted parts are very similar. Also, the micro-hardness of normalized part is very uniform on both transverse and building direction. However, the micro-hardness of normalized selective laser melted part is much lower than the micro-hardness of as received part, which is due to the phase transformation from tempered martensite to ferrite plus pearlite. For the wrought part, the Vickers micro-hardness line scan was conducted on transverse and rolling directions, and the results are very similar on both directions. Also, it becomes more uniform after the normalization process. What we found, the average micro-hardness of normalized wrought part is higher than that of normalized selective laser melted part. This may be related to the higher carbon concentration in the wrought part, since both normalized selective laser melted and wrought part have the same microstructure, with similar grain size. So as we mentioned before, the carbon concentration of selective laser melted part is 0.153 weight percent, while the carbon concentration of the as received wrought part is 0.2 weight percent. In the following slides, we are going to talk about the characterization results for the carburized, selective laser melted, and wrought parts. As this slide shows, the two-stage carburizing process, boost plus diffusion, was used. In the boost stage, the carburizing is at 925 degrees Celsius with 1.1 weight percent carbon potential for 300 minutes. In the diffusion stage, the carburizing is at 850 degrees Celsius with 0.85 weight percent carbon potential for 30 minutes. After carburization, the samples were quenched in agitated 49 degree Celsius oil. This slide shows the carburized selective laser melted and wrought parts. For the selective laser melted part, as we mentioned before, one sample was sandblasted after the deposition, the other one is not sandblasted. The XRD analysis was conducted on the surfaces of carburized selective laser melted and wrought parts. It can be seen that the XRD patterns are very similar for these three parts. Martensite, returned austenite, and iron oxides were identified for all of them. The carburized selective laser melted and wrought parts were cut, mounted, ground, polished, and analyzed by the optical microscope on the cross-section. This slide shows the cross-section optical micrographs near the carburized surface. So the intergranular oxidation was found near the surface for both carburized selective laser melted and wrought parts. The higher magnification micrographs were used to measure the thickness of the IGO layer for these three parts. And we can see the IGO depth for selective laser melted and wrought parts are very similar to each other. Like it's about 12, 11, or 14 microns. Carbon concentration can be measured by OES, like we did before for the as received parts. The carbon concentration profile can be measured by removing a measured layer one by one. At the same time, we need to measure the sample thickness to calculate the distance from the surface. Then we get the carbon concentration profile as this slide shows. So the carbon concentration profile of carburized selective laser melted part and wrought parts are both measured from the present work. And we can see the carbon concentration at the core is higher for the wrought material, as we mentioned before, because the core is not affected by the carburizing process. Then the wrought part near the surface, the carbon concentration profile is very close to the selective laser melted part with sandblasted. So without sandblasted selective laser melted part, show higher carbon concentration, a little bit higher. carbon concentration profile compared to the wrought and sandblasted selective laser melted part. The Vickers microhardness profiles were measured from the surface to the core for the carburized selective laser melted and wrought parts. So in general, the microhardness decreased from the surface to the core for all the carburized parts, which is related to the carbon concentration decrease from the surface to the core. Comparing the microhardness profile of selective laser melted part with the wrought part, the main difference is the core hardness, I think. So the wrought part show higher core hardness than the selective laser melted part, which is due to the higher carbon concentration in the wrought material. We also use the CARB tool to do the simulation on the carbon concentration profile for the current carburizing process. First, we use the default mass transfer coefficient, which is 10 to minus 5 centimeter per second. And we found the result is a little bit higher. The carbon concentration profile is a little bit higher than what we measured by OES. Then we make some change on the mass transfer coefficient. We decrease it. Then we get a good agreement with the result for the selective laser melted and wrought part. So which shows like how can we use the CARB tool to simulate the carbon concentration profile and get the good agreement with the experimental results. And also we summarize like the data we got for the carburized parts. And we can see the Rockwell hardness on the surface, like they are very close to each other. The main difference is on the carbon concentration at the core. And actually the unsandblasted selective laser melted part get higher carbon flux, which means it takes more carbon during the carburizing process, which may due to the pores on the unsandblasted sample, because sandblast can close the pores on the surface for the selective laser melted part. Let's summarize today's presentation. The as received 8620 selective laser melted part was characterized and compared with the as received wrought part. We found the microstructure is different. For the selective laser melted part, we get the tempered monazite, but for the wrought part, we got the pearlite plus ferrite. That's why we conducted the normalization process to minimize the effect of the pre-carburizing condition. Then the normalized selective laser melted and wrought parts were carburized. And we did the branch-hard grinding before the carburizing process to get a better surface finish. In general, the carburized selective laser melted part is comparable to the carburized wrought part. However, the lower carbon concentration, which is due to the decarburization from the selective laser melting process, causes the main difference on carbon concentration and microhardness at deeper carburized case. At last, I want to thank the support of the Center for Heat Treating Excellence at Worcester Polytechnic Institute and the member companies. Also, the special thanks to GKN for fabricating the selective laser melted part and Caterpillar for conducting heat treatments. So the authors would like to thank Dr. Olga Rowan from Caterpillar for the valuable suggestions and assistance on the carburizing process. Thank you. And if you have any questions, please contact Professor Sisson or me at WPI. Also, you can visit CHT website to see our interesting heat treatment related research we've done.